Hi everyone, good afternoon. My name is Yaniv Kunda, and I'll present our migration of a very important product to the cloud. So a little bit about myself. I was deployed in 1978, quite a while ago. I love technology. I've been programming since I was a kid. I have 3 kids, but only 1 wife. And no, it doesn't appear to be scalable. And I've just celebrated my 4th year at Akamai, doing mostly big data and technology around it. Very exciting, very interesting. So this is a very good example of a complete misuse of a large language model, because you're going to hear a lot about it, but not here. So it's just my contribution to the trend. But I'd like to just give you a few pointers. So we're going to talk about simple concepts that can help you build a scalable and flexible architecture for a data pipeline, protect your system against all sorts of provider issues, and reduce cost, preferably at the start of your journey, but like most, during and after. So a little bit about Akamai technologies. Akamai is one of the world's largest CDN. We provide delivery, security, and lately cloud computing. Our edge network, which serves content to all around the world, consists of really a lot of servers in many, many locations and in 135 countries. And a very interesting fact, about 30% of global internet traffic passes through the edge network. And this traffic is constantly increasing. For the last few years, ever since COVID, it's been even further increasing, but we've reached, like last year, a peak of 250 terabytes a second. That's a lot of data. And while this is very large and interesting, we're focused on the CSI Group. What we do at CSI Group is cloud security intelligence. So we have many security applications, and we at the group provide several security products, but also the platform on which these products run. This platform also serves more groups, but we're going to talk about us. So our platform ingests security feeds containing security events from various sources, process them for intermediate or data lake access, and it's used by both security products, either for analytic purposes, for end-to-end mitigation and user notification, et cetera, and for research, future product development, investigations, and other interests. So our platform needs to handle and handles very big data. What is big data? Our largest feed, which is from our web application firewall, a very popular and widespread product, contains about almost 1 gigabyte per second of compressed data. And it's varied across the different times of the day. And in special occasions, like when Yves Saint Laurent does a collaboration with a sneaker company, a very important event, peaks can be double and sometimes even triple. That's a very crazy amount of data. We process about 1.6 million records per second. That's singular security events. And that used to run on our legacy architecture. So we have a Cloudera deployment, which is a commercial Hadoop deployment on 2 on-premises locations. Each DC has more than 1,000 servers with many cores, large disks with fewer RAM, and smaller but faster SSDs with more RAM. And we use very known technologies, HDFS, Spark for processing, even some MapReduce, and quite a few proprietary technologies. So this architecture begins at data coming from consumers surfing the web and reaching our edge network on one of the 365,000 servers spread all over the world. Akamai has an internal network that runs a log collection system, which collects logs from these servers. And then these logs are transferred to our system. We have a distribution layer that collects those logs and passes them to 2 layers, batch layer for historical data and speed layer for real-time or near real-time data. The batch layer writes its data into HDFS and with indexes stored on Postgres. This is using a file format which you might have heard of in a previous Akamai lecture. But this is the very first and second incarnation of this format. And the speed layer writes its data into a proprietary in-memory database, which is called Endor. The latency on those 2 layers is 60 minutes for the historical or batch layer, and 60 seconds for the runtime, for the near real-time layer. And we have a serving layer which combines the data from the 2 layers, historical data and recent near real-time data, for returning the results to the user. This architecture is commonly known as the Lambda architecture, and it's been a while. The analytics products and incident report teams use the same layer to get data presented to the user, act upon, and that's the path our data go through. So what's so bad about the architecture? First of all, scaling out is slow and difficult. Our teams managing the network they need to do very complicated stuff like procurement, and it takes a while, it costs a lot, and it's not as easy to plan in advance. Elasticity within the infrastructure is very limited. We have fixed resources that are basically tuned to the max peaks we are supposed to handle, which is a waste of resources essentially. And we try to manage the different applications on those resources using queues, which is not automatic and not very easy. We also use the proprietary technologies I mentioned, which work well, but are hard to maintain and are not community-driven. When bugs occur, and they sometimes occur very rarely, it's not very easy to troubleshoot. So when thinking about migrating this architecture to a new one, we need to have met several requirements. So we wanted everything to be cloud-based, everything that's within our management. We have other Akamai networks that send us the data, and we have other Akamai networks querying the data, but we wanted everything we manage to be cloud-based. We need to support the same SLAs, but also enable product growth and traffic growth. And it should be simpler to manage. Lambda architecture has its deficiencies, multiple code bases, and using many open source or managed components. We have communities helping with this. we found out that ingesting a lot of data is not very trivial. A lot of ingest technologies refer to data as a stream of events, and it's very easy to think about it, but it doesn't come in the same performance as handling bulk. And existing solutions for ingest weren't good enough. We did some POCs, and performance was not good enough. Processing data previously on HDFS, which is a more file system-like storage, was relatively easy because we partitioned by timestamp, and so our applications could run on scheduled basis, running on 1 hour at a time. And ADLS on Azure provides the same benefits, but it's pretty expensive. It costs on 4 megabyte boundary packets, and it's not as cost efficient. And it also pulls us back to the same scheduling way of processing data. On the other hand, storing blob files is very simple, but how can our consumers access this data? And so when we thought about messaging solutions and how we can notify our consumers, our off-the-Azure-shelf messaging solutions weren't not good enough in terms of performance. So our new architecture is built on 2 technologies on the data side. Azure Blob Storage, which includes ADLS on some parts, and Confluent Kafka. And everything that processes data runs either on Kubernetes or on Databricks. And that's the way it works. So similarly to our last architecture, traffic comes from our edge network and arrives at our HTTP receiver layer. This is the first component touching our data. This layer aggregates, well, not aggregates data, but accumulates data and writes it to files on blob storage, and then produces a message to Kafka, to a specific topic, referencing this file. Now, the next, and this stage is very fast, relatively. We need to uphold to a SLA of our log collection network of 2 seconds, and we do it in less than 1 second. And we write files averaging at 5 megabyte size in Avro format. Now, the next stage reads these files and does a lot of work. It decodes the data because each feed might be in a different format. It parses it, and then it can either filter it, transform it, and filter it again with a configurable set of components, different for each field. This entire pipeline is just an example for one feed, but it's a pattern that repeats itself. This stage increases the latency to about 20 seconds per iteration and produces slightly larger files, still Avro format, but it's still on the realm of near real-time data. And we'll get back to this a bit later, maybe sooner than you think. And so the next component in line, called Gamora, if you notice, we have a habit of calling components after characters from various comic. So Gamora reads the data produced by Yondu, accumulates it into even larger files, but also begins to partition data. So depending on its configuration, it can partition data to different fields. And for example, an hourly time step, like in other products we run. And this layer has an iteration time of about 1 minute and produces much larger files. So these type of files are much more suited for big data access and analytic type of access. But it's still Avro. So this ingest pipeline ends with the last component called Nebula. And opposed to the previous components, which are Java application, this is the first Spark application employed here. And it does basically the same job as Gamora, but it also writes the files as Parquet files, which are better suited for analytic queries. This is a much larger latency, but again, much bigger files. And this is the first use of ADLS storage, which is well, off the shelf, good enough for most analytic engines. So off of this pipeline, we have several points of exit, like a savings account. And we can use each stage with its different latency and file sizes to different purposes. And this is like a delta-ish architecture, like the bronze, silver, and gold stages of data, only this is basically the same data, just not structured, not different data, but structured, better suited for different types of applications. So what do we do with this data? For example, the Yondu output, which is a latency of 10 seconds, we can use for our near real-time applications, such as security event notification for our users. And the output of the next stage, we can use for batch applications like client reputation, which eventually goes out back to the edge and mitigates dangerous clients. And both of these can be used for different analytic applications, more like near real-time and more batch on Databricks, which have ingest jobs, indexing data, and writing it to a dedicated storage account. And on the query side, we can query this data on Databricks using our API gateway, which serves our customer-facing applications. Our data lake data is also ingested into, well, not ingested, but accessed by Databricks directly, since it's already in a format suited for analytics. And that is mostly used by our research teams. So you've noticed the extensive use of Kafka here. So how does Kafka help us? We chose it because, well, the way it works is we write a file and produce a message for it. When we don't store the actual data. So it's just a metadata, which contains a reference to the file and some statistics, either a number of rows or even a histogram of row counts per specific fields, configurable for each application. And the applications have a simple flow. They consume message from an input topic, read the reference files, process, and write their output files, and then produce an output message to the output topic, or messages in some cases. And all of this is done in a single Kafka transaction, which provides fault tolerance and exactly once semantics. So what do our most Kafka users use Kafka for transferring data? And, well, they don't do much, because you can see we have a very high cluster load of, I think it's about 1%, and our throughput can be handled by very old modems, and not much data, not really much. This is not big data. This is just big metadata. So it's not much, but performance testing showed us that to process the data itself, we need a lot of pods, and each pod has its own consumers that need to read the Kafka messages. And to enable parallelism in such a big consumer group and have room to grow, we need to have many, many partitions for each topic. And so our cluster, our production cluster has about 10,000 partitions. And we need those brokers to sustain many concurrent connections from those consumers. On the analytics side, as you've seen, we've used Databricks. And it was easy because most of our applications were Spark applications. And it's basically the same syntax. But the biggest benefit was that one of my colleagues called it Spark on steroids. And well, Databricks is not just a managed Spark. It's a very optimized Spark and continuously optimized. And we have the Photon engine, of course. So developers need to think less about optimizations and more about product business logic. In addition, it revolutionized our research team's workflow because, well, it's kind of embarrassing, but they've been using queued Hive queries that at best took forever and at worst just stuck, which basically is the same. And when that didn't work, they just transferred files from HDFS to their local PCs or Macs and processed them locally, which maybe today with things like DuckDB is better, but this is kind of ancient. And they moved to using notebooks, easy to manage, provisionable, and all sorts of ML tools used within the Databricks community, and they've really expanded their usage of our data. Along the way, we encountered several problems. So I've talked about Kafka's, our use of Kafka's transactional API, but it's relatively simple, but it does require some boilerplate coding. So we developed a shared library between all of our applications, and it can be used to manage this entire thing. We call it Kafka Transaction Manager, a very original name, but it does everything we need. The entire lifecycle management of consuming messages from the input topic, processing the messages by the application, and producing messages to one or more topics, and managing the entire offsets for either when a transaction is canceled or committed. Another problem we faced, well, nobody really knows our architecture. It's publicly revealed maybe in previous sessions, but it's not very common, so nobody knows about it, especially not Spark. And our applications still need to access it, and most of them are Spark-based or Databricks-based. So we developed a Spark data source V2 implementation called the Kafka Blob connector. And besides of handling the entire read a Kafka message and read its files, it can filter messages according to timestamp using pushdown, and assign files to the task using several strategies. Simple one is one file per task, which is mainly for prototyping, and optimizing the files for maximum task size when you want to utilize the full memory, or for a number of partitions when you have a very elastic workload and you want to use the most of your resources. Or in a better example, doing a dynamic number of partitions that can be controlled using a Kafka lag. So it scales up when necessary. Another problem, which is something we anticipated from the numbers, but it was much more severe than we did, is throttling on the storage, cloud storage we used, Azure. And the basic solution is to spread data across different storage accounts, commonly known as sharding. And we use a simple, consistent algorithm, which is called the modulo. We use our customer ID to spread their data across different shards, but each customer has its own shard, is located on a single shard. So Java apps can write data to different storage accounts and different Kafka topics, and the message indicates on which storage account the file resides. And Databricks, which is limited in the sense of it can't write to different storage accounts, is read using different ingest clusters. So instead of ingesting the entire data on a single cluster, we have several smaller clusters. And we write the index data, each ingest cluster writes its own index data to different data tables on different storage accounts. So at the end of this path, our API gateway can create a query according to the specific table that the customer data resides on. The last problem I'll mention is that Databricks clusters can get stuck or crash, which, of course, hurts our customers. So we provided an embedded mechanism in our API gateway called the Databricks Load Balancer, not to be confused with the Databricks Load Balancer, but let's call it the Databricks Smart Load Balancer. What it does is split work between different smaller clusters, and it tracks the cluster health, which provides us better fault tolerance. In addition, using configurable customer-to-cluster mapping, which will fall back to automatic configuration, provides cache affinity, also talked about in one of Akamai's presentations, which makes everything much faster, query-wise. It's also theoretically supports asymmetric load balancing, so we can dedicate larger clusters for larger queries. I want to talk about cost reduction because, as I said, you should probably think about cost in the first place, but sometimes cost can hit you a bit later. And we've employed several things to reduce our cost. So this is just a few tips for you. Z standard compression, a standard that developed by Facebook and been a while for a couple of years, I think. We've used that instead of the default snappy compression and achieved 30% smaller files, so 30% smaller than snappy. And the compute increase was really negligible. Smart eager retention. So in our architecture, we have our Kafka messages pointing to blob files. And Azure Blob Storage has a lifecycle policy management, aka retention, which works well, but it can be configured in resolution of days. So the minimum number of days a blob file stays in place is at least 1 day. And this ingest pipeline has a latency of seconds or minutes. And so it comes out that we have a lot of data residing on blob storage, which no one needs to access because it was already accessed, processed, and done with. So we have an application that uses the messages we produce to Kafka, containing all the statistics. And we can determine if a file has been read by all its consumers by processing the Kafka log and, of course, having some grace period in case something went wrong. So it determines the files that can be deleted and then deletes them from blob storage, reducing cost significantly. Databricks Smart Scaler. So scaling Databricks clusters can be done automatically, but it can use just simple metrics like CPU and network or memory. And that's not that sometimes is not the best case for real-world scenarios. So we enabled a load balancer. We wrote a load balancer that can listen to Kafka lag and scale our Databricks cluster externally using the Databricks API. It can also be used to scale the cluster in specific time periods where we have less traffic at night and on weekends. So saving some more cost. So if I can sum up everything that you can take away from this presentation. Use a simple architecture, the simplest that fit your needs, but try to think about future ones. Don't be afraid to use low-cost storage. It has its issues. It's not as performant as SSDs or RAM, but if it fits your purpose, use it. You can use it several times for different purposes on the same data, and it still might be cost-effective. And employ smart metadata to track it. That provides a very flexible backbone for many use cases. Not for all. There isn't any single architecture that fits every need. Another advantage of this architecture is that it can be developed in an incremental way. So we can start off with the lower latency data sets and use them. And while working on the longer latency for different products, this data is still available for lower latency applications, which can provide better time to market. And of course, read everything you can about your provider's service limits and prepare for workarounds, if possible, in advance. This will come in form of availability issues. And please use sharding everywhere. It's not a big mess. It solves many, many problems. Also, there's nothing wrong with proprietary technology. It sometimes works for years after its developers went through different places. But if something goes wrong, you don't have a community support. Knowledge is sometimes passed through and diluted. So if you do develop proprietary technologies, try to make it simple and limit its scope. So instead of a complete system for a database, a complete database, you can use a simple conceptual architecture or a simple library component that can glue everything together. And of course, cost. Cost is everything. We can't exist as businesses if we're not cost effective. If you want to learn anything more about what I've talked about and what my colleagues talked about in previous sessions, last year in the summit and in Kafka Summit, and of course our own sessions here at the Summit 2023. You can find us online. And with that, thank you very much.